Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this is the entropy of mixing, and the section in the textbook is 13.3, and it's also good to read the special section at the end of the chapter. Alright, so here are the learning outcomes. At the end of this, you'll know how to calculate the change in entropy due to mixing of gases. You'll understand why there is lost work potential when gases are mixed, and you'll be able to calculate the work required to purify a gas. Right, so let's talk about the entropy change of mixing, and this is a figure from the textbook. And what we're looking at here is we have a partition in this box. We have oxygen on one side, pure oxygen, at 25 C and 200 kPa, and then we've got CO2 on the other side, also at 25 degrees C and 200 kPa. And the question is, well, what happens to the entropy if I remove this partition? Now, since these are both at the same temperature and the same pressure, I wouldn't expect there to be any change in temperature and absolute pressure in here. So in fact, if I was to look at what my change in entropy is, and assuming these are acting as ideal gases, and at these conditions both oxygen and CO2 would act ideal, I have this equation that I've written up here. So I've got the mass of oxygen, and then Cp ln of T2 over T1, assuming a constant heat capacity, and then I've got my pressure term. Now the thing to note is that this is the Cp and the R of O2 in this first term, and this is P2 of oxygen. This is the final pressure, but remember these are the partial pressures. So this is the initial partial pressure and the final partial pressure. And then I've also got to account for the change in entropy of the nitrogen, so I have a similar term written down here, but again this is the partial pressure of nitrogen at the final state. Now T2 over T1, those are the same, so that term right there is going to be 0, and this term right there is going to be 0. So this simplifies down a little bit. And so now I've got zeros for those terms. And then what I've done is the final partial pressure, assuming this is an ideal mixture, is just going to be the mole fraction at the end times the total pressure. And those pressures right there are going to cancel on each one of those terms. And so what I end up with is finding out is that the change in entropy is going to be the mass of the oxygen, and I've got minus R ln of YO2. So it's just simply the natural log of the final mole fraction. And then I'm going to add m of N2, and this is minus R ln of Y2. And if I'm doing this in mass, these are going to be the R values for each of the particular materials. If this was in terms of moles, this would just be the universal gas constant. Now note that the final mole fraction is always going to be something between 0 and 1, so it's going to be a fraction. And so I take the log of a fraction, that's a negative number, and this minus sign here. So this whole thing, delta S, is going to be greater than 0, which I would expect the entropy should increase. So now if I wanted to kind of look at just maybe put some numbers in here, let's say I started off with 2 moles of oxygen and 3 moles of CO2, then I could look at what my mole fractions are over here. So now I'll write this down in terms of number of moles of O2, and it would be minus R, and the natural log of, well, the mole fraction is going to be simply 2 over 5 after it's mixed. And again, those are universal now, and so then the number of moles of CO2, which was 3, and then I've got minus R universal natural log, and that's going to be 3 over 5. And so I can go ahead and determine what that change in entropy is going to be upon mixing of those two gases, even if the temperature and absolute pressure doesn't change. All right, well, there's got some interesting implications of this, of things that you can do. And so let's do a little bit of review if you don't remember about osmosis. So what we have here is a picture of a beaker. This is from Wikipedia, where we've got a salt solution. This is what this is. We've got water with salt molecules in it. And on one side, the salt is more diffuse than it is on the other side. And so and then I've got in between this is a semi-permeable membrane. The salt cannot go through, but water can. But what's going to happen if I was to fill this beaker with the same height on both sides is pure water is going to go through that membrane, causing the right-hand side to go up. And it's going to do that until we get effectively what's called the osmotic pressure balance at this point right here. And so that's the idea of osmosis. And it turns out there's actually a lot of work potential that goes on, or actually lost work potential when we do this mixing, that it would be nice to be able to utilize. And if you want to think of a point where we've got pure water mixing with salt water in large amounts, you know, it happens a lot in Alaska, it happens a lot the world over, which is where we've got freshwater streams that are emptying into an ocean. So I've got pure water mixing with salt water. And because it's generating entropy when it does that, it's actually generating, or it's destroying exergy. Because remember, the exergy destroyed, remember this, is T naught S gen. So anytime I generate entropy, I know I'm destroying work potential. So somehow I'm destroying work potential when I do this mixing. It'd be nice if I could extract that energy. And it turns out you actually can. You can generate power plants based on this idea. And so this is kind of the general idea. Is I'm going to put a semi-permeable membrane in between the freshwater stream that's emptying right into the ocean. So let's draw it on the side here to kind of get this idea of what's going. So this is my river. So this is fresh water. And this is emptying into an ocean. And these are all at the same height at this point. And what I'm going to do now is I'm going to go ahead and build a wall right here. And then I'm going to go ahead and place a semi-permeable membrane in between the river. And then I'm going to have ocean water on the left-hand side. So the river is going to come up here, go through a semi-permeable membrane, and the ocean water is going to build up. So I can put a little wall there as well. And at some point, and if I have this wall below the osmotic pressure, the water will come over this hill. And imagine I can just put like a water turbine over there to go ahead and generate some power. And depending on how high that is, I could generate power just simply from mixing this pure water in with the ocean. Right? And although this looks like a great idea in theory, you might wonder if you can do it in practice. And actually, you can do it in practice. And so let me pull up a website here. This is an article from New Scientist about 6 or 7 years ago, where the first osmosis power plant went on stream in a fjord in Norway. And so it's kind of a short article. If you want to look at it, you can. But one of the kind of interesting things is to see what the osmotic pressures that are generated. And if you look down here, it tells you it's equivalent to a water column 120 meters high. So you can imagine having a dam that's over 100 meters high. It clearly can generate a lot of power. And there's a lot of water that's going in the emptying of rivers into the ocean. So if you wanted to know how much power we could generate, well, the amount of work that I could do power is going to be the mass flow rate of material that's going in times whatever that temperature is times the entropy that is being generated. And so all I need to do is calculate how much entropy is being generated by mixing these, and we just did that on the previous slide. You can get an idea of how much work you actually could get out of one of these power plants. And you'll do a homework problem and you'll realize it's actually quite a lot of power. So here I want to do an example problem. We're going to turn this around a little bit. Instead of mixing things, what we're going to do is we're going to purify. And so here's the question. I want to go ahead and purify helium. And if you've ever wondered where helium comes from, since it's a very inert gas, it's not like attached to minerals or anything like that. It's actually just dissolved in natural gas. And so there's actually a finite amount of helium. That's a helium market, which is sort of interesting. But helium is purified from natural gas. And most natural gas, where it occurs naturally, it's on the order of about 0.45 molar percent. So it's not a lot. So kind of like this figure over here, if you imagine the blue is natural gas, helium is very small. It's like those little teeny red dots. And what I want to know, if I want to go ahead and purify helium, I want to get pure helium, I want to extract it from here, what's the minimum amount of power that would be required in order to do it? And so what I'm doing effectively is changing my natural gas to pure natural gas and pure helium, some small amount of pure helium. And so, well, we know that the amount of work is going to be T naught S gen. And so I want to figure out how much entropy I'm generating. So what is the change in entropy? And the change in entropy is going to be the change in entropy of the helium as it becomes purified, and the change in entropy of the natural gas as it becomes purified. And so each one of those terms, if we assume there's no temperature change as we go on, we're going to have that natural log of the partial pressures. Well, the natural gas term is going to be the natural log of, well, the final is going to be 1 mole fraction, and the initial is going to be 0.9955, and that right there is about 0. So there's actually not much entropy change in the natural gas. The one that really matters is the helium. So we'll just focus on this first term right over here. So the change in entropy is going to be, we'll do this on a per mass basis, is going to be minus R, and the natural log of 1 over 0.0045. So this is the final partial pressure over the initial partial pressure in terms of mole fraction. So I've got 1 over the mole fraction there. So let's go ahead and put in some numbers in here. This is going to be minus, and this is R of helium, and so R of helium is 2.077 kilojoules per kilogram Kelvin, and I'm going to do the natural log of 1 over 0.0045, and so my change in entropy here, now this natural log term is going to be a positive value, which means that my entropy goes down, which I would expect. This is a process where things are becoming more ordered, and that becomes minus 1122, and the units on that are kilojoules per kilogram Kelvin. So that's how much I've decreased the entropy. So now let's figure out how much work this is going to take. And so this is actually the minimum work. It's going to be P naught delta S, and so let's just assume this is happening around room temperature, or 298 Kelvin, and this is going to be 11.22 kilojoules per kilogram Kelvin, and that number right there comes out to 3343 kilojoules per kilogram. So that right there is the minimum amount of work that would go into this purification process. And clearly any inefficiencies in the process would just increase the number. But now I've got a general idea. And we can kind of put a price now on what the minimum price should be on helium.